I'm rounding off the rate of chemical reaction with the collision theory. So the question now is, what does the collision theory state? It states that the reactant molecules must collide effectively for a reaction to take place. For a reaction to take place, there must be an effective collision between the reactant molecules. But what does it take for this effective collision to take place? 1. The reactant molecules must collide with sufficient energy, which is equal to or greater than the energy barrier, and they must collide in the correct orientation for the collision to be effective. An effective collision definitely results to the formation of products, while an ineffective collision does not result to the formation of products. This means that for a reaction to take place, there must be an effective collision between the reactant molecules. And for effective collision to take place, the reactant molecules must have enough energy to overcome the energy barrier. And not only that, they must have enough energy, they must also collide in the correct orientation for that to result to the formation of product. Else, no new product will be formed, and such collision is referred to as ineffective collision. The energy barrier that should be overcome before product is formed is referred to as activation energy. And so we define it as the minimum amount of energy required for a reaction to take place. Remember, the reactant molecule's energy must be equal to or greater than the activation energy for that reaction to take place, for an effective collision to take place. So we say that it is the energy that needs to be overcome, a hill that needs to be climbed by the reactant molecules before they will finally form products. But you must note that for new product to be formed, that bonds are broken and new bonds are formed, and that the bonds that should be broken are bonds of the reactant, while the bonds of products are formed. So in every chemical reaction, bonds are broken and new bonds are formed. Also, chemical reactions that have low activation energy are spontaneous at room temperature, while those that have high activation energy are not spontaneous, and so they need energy for them to be spontaneous. And this energy can be in the form of light, in the form of heat, or in the form of electrical energy. Once they are supplied, then the reaction will take place. It must also interest you to know that catalyst alters the activation energy of a chemical reaction. In other words, it changes the activation energy of the chemical reaction, and this change can either be by increasing the activation energy or by decreasing the activation energy, and this depends on whether the catalyst is a positive catalyst or a negative catalyst. Positive catalyst decreases the activation energy, that means it lowers the activation energy, making the reaction to be fast or gets to completion faster, while negative catalyst increases the activation energy, hence elongating the time taken for that chemical reaction to get to completion. There are several factors that affect the rate of chemical reaction. These factors include, as I've just mentioned, catalysts already. We also have concentration, temperature, pressure. Now I'm leaving you with a video which clearly explains how these factors affect the rate of chemical reaction. How these factors can make a chemical reaction to be either fast or to be slow. I'll come back at the end of the video to round off the lesson.
In today's video, we're going to look at the factors that affect the rate of chemical reactions. So temperature, concentration or pressure, surface area, and the presence or absence of a catalyst. Before we can understand how these factors affect the rate though, we need to cover the theory behind reactions, which is known as collision theory. This states that in order for particles to react, they have to collide with each other with sufficient energy, which we call the activation energy. And if they collide with less energy than this, then nothing will happen. They'll just bounce apart again. So if we were to think about an entire reaction, which will involve tons of particles, then the rate at any particular point is going to depend on two main things. The most obvious is the amount of energy that the particles have. The more energy they have, the more energy they can transfer during the collision, and so the more likely they are to surpass that minimum activation energy. The other important thing is the frequency of the collisions, which just means how often the particles collide with each other. So even though not all collisions are successful, because the particles involved don't always reach activation energy, the more often they collide, the more successful collisions there'll be overall. Now, whenever you think about how these four factors affect the rate of a reaction, you always want to think in terms of how they affect the amount of energy that the particles have and the frequency of the collisions, as increasing either of these will increase the rate of reaction by increasing the number of successful collisions. Let's start with temperature. As the temperature of a reaction increases, the particles gain more energy, which means that they move faster. And because they're moving faster, they'll collide more frequently. They'll also collide with more energy each time, so are more likely to exceed the activation energy. So overall, there will be a higher rate of successful collisions, and thus a higher rate of reaction. Now, concentration and pressure are normally considered as a single factor, because they both refer to how many particles there are per unit of volume. It's just that concentration generally refers to solutions, and pressure refers to gases. When either of these is increased, it means that there'll be more particles per unit of volume, which makes the collisions more frequent, and so increases the rate of reaction. Just like concentration and pressure, a higher surface area will also increase the rate of reaction. For example, if we wanted to react 3 grams of magnesium with an acid, we could use a solid block of magnesium, small chunks of magnesium, or powder. As all of these have the same mass and volume, the powdered form would have the highest surface area to volume ratio, and so would have a much higher area over which collisions with the other reactants, in this case the acid, could take place, meaning that the frequency of the collisions would be higher, leading to a higher rate of reaction. The last factor that we need to cover is the presence of a catalyst. Catalysts are substances that speed up a reaction without being used up in the reaction themselves. So we don't include them in the reaction equation, as they're not reactants or products. To understand how they work, we can use now this distance between the reactant's energy level and the very top of the curve is the activation energy, which remember is the energy that the collisions have to have before they can react successfully. What a catalyst does is lowers this activation energy by providing an alternative reaction pathway. And this means that there'll be a higher proportion of successful collisions. The word catalyst is actually a pretty broad term, and a whole range of different substances can act as catalysts in different situations. One of the most common sources of catalysts, though, are the transition metals, like cobalt and nickel. And if you do biology, you'll have come across them in the form of enzymes, which are just catalysts made by living organisms.
Welcome back. In conclusion, the factors that affect the rate of chemical reaction include temperature. Increase in temperature increases the rate of chemical reaction because the reactant molecules have an increase in kinetic energy as a result of that increase in temperature. They collide more, resulting to more increase in effective collision as well as increase in the rate of reaction. But a decrease in the temperature decreases the average kinetic energy of the reactant molecules, decreasing their rate of collision, as well as decreasing their rate of effective collision, and greatly decreases the rate of the reaction. Now let's look at concentration. Concentration and pressure go together. Concentration is for those in solution, while pressure is for gases, but they all talk about the amount of substance or amount of reactants present per given volume or per given area. Increase in concentration increases the amount of the reactants per given volume. That increases the rate of collision as well as the rate of effective collision, which results to the rate of increasing rate of reaction. A decrease in concentration decreases the rate of collision based on the fact that there is an increase in the distance between the reacting particles, hence decreasing the rate they collide effectively also decreases the rate of the reaction. Now the third factor is surface area. Increase in surface area increases the rate of reaction, while decrease in surface area decreases the rate of reaction. Let's look at light. Reactions that are affected by light are referred to as photochemical reactions, and we have example in the reaction of the alkane, the saturated substitution reaction of the alkane, which are saturated hydrocarbon, by the halogens. If methane reacts with chlorine, the chlorine atoms keep replacing the hydrogen atoms in methane until it is completely replaced to form tetrachloromethane. That reaction is catalyzed by light. We also have other reactions that are catalyzed by light. This presence of light makes that reaction to be faster, else it would have taken a longer time if it didn't take part in the presence of light. It may take a longer time or it may not even happen at all. Then for nature of reactants, some metals react differently, though they are all electron donors. They react differently with water or with dilute mineral acid. The ones higher in ECS, higher than hydrogen in ECS, reacts with dilute mineral acid to produce a hydrogen gas, although copper is an exception because it can also react with conc HNO3. But those above hydrogen reacts with hydrochloric acid to produce hydrogen gas, while those below hydrogen in ECS do not react with dilute mineral acid to produce hydrogen gas. Also, metals react with water in different forms. The strong metals like potassium and sodium react with water in the cold, while the moderately reactive metals like magnesium, zinc, iron, they react with steam, while the ones below hydrogen like silver and gold do not react with water in any form, whether in the cold or in form of steam. Now for the catalyst, as I said before, alters the rate of a chemical reaction. That means it can either increase the rate of chemical reaction or decreases it, but that depends on whether it is a positive catalyst or a negative catalyst. We have several catalysts, especially the transition metals, which are the ability to exhibit variable oxidation state, either by increasing the rate of chemical reaction or decreasing it. Like in contact process, which is the industrial preparation of H2SO4, vanadium 5 oxide is used. In Haber process, finely divided iron is used. In hydrogenation, nickel catalyst is used. In polymerization, trace of oxygen is also used, and a host of others where different elements, especially the transition metals, are used as catalysts. In the laboratory preparation of oxygen using potassium triiosochlorate 5, manganese 4 oxide is also used as a catalyst. Now this is where we are going to draw the curtain for today. I'm glad you stayed with me to this end. Endeavor that you give your best shot in the quizzes, and see you in my next class. Thank you very much.